Hello, let us continue. Today we'll be doing some recap of what we did in modular arithmetic, just the introduction part of modular arithmetic, where I was defining terms, and then just the beginning of modular arithmetic. Now, so I began by this definition, where if m is any positive number, m is any positive number, when do we say that these two numbers are congruent? So I said that these two numbers A and B will be congruent mod M if M can divide their difference. If M can divide their difference, then we say that they are congruent. Now, if M cannot divide their difference, if M cannot divide their difference, then we say that the two numbers are incongruent. They're not congruent. That's what we mean. If M cannot divide their difference. So this M is then called the modulus. M is called the modulus of the congruence. Now that is the definition of congruence. And this is how we write it. If A is congruent to B, then we write it this way. A is congruent to B. Mod M. Mod M. If it's congruent, A is congruent to B. And we know what this means. We've just said that we say that these two numbers are congruent. A is congruent to B, mod M, if M can divide the difference between A and B. I'm using this symbol to mean divide, and that's what he said. For instance, I can say 2 can divide 8. 3 can divide 9. So that's how we write it. It's not the same as this, because this one means 9 divided by 3, 8 divided by 2. This is different. So this one, I'm just saying 2 can divide 8 and there'll be no remainder. 3 can divide 9 and there'll be no, so this is how we write it. And so we're saying that A is congruent to B mod M if M can divide the difference between these two numbers. That's what I mean by two numbers being congruent to each other. Now, so this is an example just to make that definition sink. For instance, we can say 10 is congruent to 4 mod M. No, mod 3. Our M is 3 in this case. 10 is congruent to 4 mod 3. And what this means is that 3 can divide the difference between 10 and 4. In fact, this difference is just 6. It's 6. 3 can divide 6. And so you say that 10 is congruent to 4. Because you know that difference, 3 can divide. What about this one? Can 3 divide the difference between 10 and 1? The difference between 10 and 1 is 9. It's true that 3 can divide 9. Therefore, we say 10 is congruent to 1 mod 3. This 3 we said we call it mod is the modulus mod. That is the divisor. That is the divisor. In this case, the difference between 15 and negative 5 is 20. And we can see that, what is the mod here? The mod is supposed to be, I was using a mod of 3. But in my working, I used 4. So when I was doing it, I was planning to use 4, but I wrote 3 here. Now, so let me just do it using 3. 3 cannot divide 20. And therefore, this one I should have written that 15 is not congruent to negative 5, mod 4, mod 3. So I think I forgot this because in my mind, I thought I had written 4. But in doing, I had written 3. So it's supposed to be not congruent. Now, I think we know what it means by two numbers to be congruent to each other. That's what it means, what I've just explained. That they are congruent if the mod or the divisor can divide their difference. Let's look at this case. 22 minus 4 is 18. 22 minus 4 is 18. The mod cannot divide 18. And therefore, this statement is true. This statement is true. That 22 is not congruent to 4 mod 5. That statement is true there. So that is the definition of congruence. And it's not the only definition. There's another definition that we'll be looking at. That is the first definition of congruence. That two numbers are congruent to each other, mod m, if m can divide their difference. That is one of the definitions. Now, when we are doing this modular arithmetic, we use any of the definitions to do our modular arithmetic. And whichever definition we use, the result will be the same. Whatever definition you choose, the result will be the same whenever you are doing modular arithmetic. So this is the first definition, and we'll be using it as we progress. Now look at this example. This example wants us to tell which numbers are congruent to 3 mod 7. Which numbers are congruent to 3 mod 7? There are many ways of looking at this question. If I was to use the first definition there, then I'm asking myself, supposing I was to write this, I'm asking myself, what numbers, if I subtract 3 from them and divide the result by 7, I would not get a remainder. What numbers are those? What numbers? If I subtract 3 from them, the result that I get will be divisible by 7. Be divisible by 7. For instance, let me see. If A is 10, is 10 congruent to 3 mod 7? So I just subtract 10 minus 3, I get 7, and I can see 7 can divide 7. So in fact, one of the numbers is 10. One of the numbers is 10. So the question is, which numbers are congruent to 3 mod 7? So there are so many numbers. There are so many numbers which, if 3 is subtracted from them, the result will be divisible by 7. So the question is saying, if I was to use the first definition, That is how I would do it. And the other way that I can do it is this. I would use the other definition. If I was to write, for instance, M mod M, if I was to write M mod M, what does this mean? M mod M, what does M mod M mean? Just rest here and write block properly. I forgot to ask whether you are hearing what I'm saying. Can you hear me?
Yes, I can hear you.
It's okay, thank you. Now, so if I was to use, I've already used the first definition to do that question. And the first definition, it has already given me one value. I've already said that what numbers are congruent to 3 mod 7? In other words, which numbers, if 3 is subtracted from them, the result will be divisible by 7. We've seen one of the numbers is 10. In fact, the other number could be 17. 17 is congruent to 3 mod 7. Because I can see that 17 minus 3 is 14. And 7 can divide 14. It's one of the numbers. But how do we get all the numbers? Because we said there are so many. So for me to get all the numbers without guessing, this one trying this and trying that, I begin to look at another way of, if somebody tells me M mod M, what does this mean? M mod M. It means that A is the remainder. The number that is here is the remainder whenever, if I had a number, supposing I had another number, then divided by M. So what is written here is the remainder that I got. That's the remainder that I got. So if somebody writes me 2 mod 7, this person is telling me that he had a number then divided by 7, and the remainder is 2. This 2 is what he wrote. So if somebody tells me 3 mod 7, what comes to my mind, this person had a number and divided by 7. The remainder was 3. It's what is written here. And so if we also look at it in that direction, it becomes easier for us. Now let's look at this in that direction. This person is saying he had a number divided by 7, and the remainder is 3. So we're just asking ourselves, which numbers, when divided by 7, the remainder will be 3. We've already said one of the numbers is 10. We said another one is 17. And when you divide it by 7, the remainder will be 3. But we're asking ourselves, which numbers are they? Because there are so many. So this is how I look at it. I assume I have a number A divided by 7. I know the result will be X, and the remainder is 3. The remainder is 3. That's how I look at it. I don't know why this one is writing in some places and refusing to write in other places. Just rest here again and rewrite. So this guy has given me 3 mod 7. So according to me, once I see this, I imagine he had a number, divided this number by 7, got a result, and there was a remainder. And this remainder was 3. This is what comes to my mind. I want to get A, I know that then A can be written as 7 times X plus this remainder. I want to get A. Then I know that A will be 7. Just if I was to use a small example, what I know is this. If I have 10 divided by 7, the result is X, and the remainder is 3. So 10 can be written as 7X plus 3. This X will be 1 in the case of 7 and 10. In the case of 7 and 10, so let me just write here, 1. That 7 can go into 10 one time, and the remainder is 3. So how do we write 10? 10 is the same as 7 times 1, then plus 3. So that is the knowledge I'm applying here. That's the knowledge I'm applying there. 10 is the same as 7 into 10 once, and the remainder is 3. So how do we write 10? 10 is then written as this divisor times the quotient. So the divisor times the quotient plus the remainder, plus, this is supposed to be plus the remainder. So this is how you get how do you call it? This is the divisor, the quotient, and I think this is called the dividend. Dividend, I think. The number you are dividing into. The number you are dividing into. It will be given by the divisor times the quotient plus the remainder. That is how we look at it. Now, the question is, how do we find these numbers? What is X? X is, this is not writing here. X is any integer. X is any integer. So what I mean by that, X can be any integer. -3, -2, -1, 0, 1, 2, 3, and so on. This was a mistake here. It's supposed to be 3. This is supposed to be not 6. It's supposed to be 3. This one is supposed to be 3. Now, so that is how we do it. Where X is an integer. So you can choose X to be -4. So if X is -4, what do you then have? A will be -4 times 7, which is -28, then plus 3, and that gives you -25. X can be -3. If X is -3, what do you get? -3 times 7 will be -21. And then plus 3, this gives you 18, negative. X can also be -2. We put -2 where X is. That gives us -14. Then add 3 to it, which gives you -11. X can also be -1. And that would be -7 plus 3, which is -4. X can also be 0. That will give you 3, and so on. These numbers are congruent to 3, mod M. And you can prove this using our earlier definition. For instance, if you have -8, no, -18, is it congruent to 3 mod 7? So if you want to use our earlier definition, just subtract -3 from -18, and you get -21. And ask yourself if 7 can divide -21. So again, I think I've emphasized the point of congruence. The point of congruence. When do we say that numbers are congruent to each other? And again, we say they're congruent if their difference is divisible by the mod. If their difference is divisible by the mod, we say that the two numbers are congruent to each other. Any question up to there? Anybody who has not understood or requires clarification on an issue regarding congruence? Anyone that requires a clarification on an issue regarding congruence and especially the definition? Because we just looked at the definition of the term congruence. And what I just talked about while I was emphasizing that is the definition 9 here, which says if you're given two integers, a and m, then when we write m mod m, it means that a is the remainder whenever a number is divided by m. A is the remainder whenever a number, or whenever a, or whenever a number is divided by m. And I've shown this example. 14 divided by 5. The remainder is what we're interested in, is 4. The remainder is 4. And so, instead of somebody writing 14 mod 5, since this number is too huge, bigger than the divisor, this is the divisor. The number here is supposed to be always smaller than the divisor. Whenever it's bigger than the divisor, you divide it and write the remainder. So instead of somebody writing this person is supposed to in fact write for mod 5. Divide by 5 and write the remainder. This number is bigger than the divisor. So instead of somebody writing 139 mod 10, what this person is supposed to be writing is the remainder, which is 9 mod 10. This number is bigger than this. It's bigger, but bigger negative. It's a bigger negative now. Of course, it's not in terms of greatness. This is smaller than this. But I am saying it's a bigger negative number. So then we divide by 5 and write the remainder. -14 divided by 5, we just do it the same way we do when there are positive numbers. And ask ourselves, how many times does 5 go into -14? Do we discover that it goes there 3 times? It goes there -3 times. -3 times. Negative 3 times this would be negative 15. Subtract the one at the bottom from the one above. When you do that, you get 1. Get 1. This is just normal division. Normal division. We know that 5 goes into negative 14, negative 3 times. The remainder is always positive. You can never say that your friend remained with your negative 10 shillings. It has to be positive. But the quotient can be negative. The quotient can be negative. The remainder, let it always be positive. You can never say he remained with my negative 20 meters of material. The remainder has to be positive. So 5 goes into negative 14, negative 3 times. And there's an easier way of doing this. There's an easier way. How do I get to know it's negative 3 times? Assuming that 14 was positive, let me assume it was positive. How many times does 5 go there? 5 will go there 2 point something, which is bigger than 0. 2 point something. Once I discover it is 2 point something, then I write here negative 3. Negative 3. Because I discovered 2 point something. That is the easier way I look at it. The easier way I look at it. I imagine, what if the 14 did not have a negative? I divide 5 into it. I get 2 point. Once I get a 2 point, I round it off. It's not even rounding off. It's not even a rounding off. I take the next whole number. I don't round off. I take the next whole number, which is 3, and give it a negative. Again, show you. Let me show you, because sometimes I find a problem. Sometimes people are unable to divide a number into a negative number using this long division, and tell me what the remainder is. They can divide, for instance, you can find people can divide this very well, can divide this very well, because it has no remainder. But whenever it has a remainder, people get a problem dividing. So for me, this is what I do. Supposing this one, so I know it will have a remainder. Assuming it did not have a remainder, I'm just showing an easier way. Assuming it did not have a remainder, 5 will go there 3 point, I think it's 3.2 or what? 3.2. Once it's 3 point something, I take the next whole number. So I would then say, and give it a negative. Because 5 goes here, 3 point something, which is bigger than 1, bigger than 3.0. So 3 point something. I take the next whole number, which is 4, and give it a negative. And then multiply this negative 4 times this, and get negative 20. And then subtract to get the remainder as positive 4. The remainder as positive 4. That's how I do it. That's how we divide a number into a negative number that has a remainder. so that you can tell what the remainder is supposed to be positive. The remainder can never be negative. In fact, I can do part E to emphasize that point. Whether you know how to divide. I'm dividing 9 into -4. Supposing 4 was positive, 9 will go there, 0 point and some numbers, 0 point some numbers. I take the next whole number, which is 1, give it a negative. So 9 goes into -4, -1 times. What's the remainder? The remainder is 5. The remainder is 5. I know you know how to subtract, because this is just subtracting. -4 minus -9. -4 minus -9. Minus times minus is positive. So what I have is -4 plus 9, which then is 5. So 9 goes into -4, -1 times, and the remainder is 5. So instead of somebody writing this person is supposed to write 5 mod 9. Supposed to write that 5 mod 9. So it's very easy dividing and writing the remainder. That's what you mean by mod. So the mod, the number coming before the word mod should be smaller than the one coming after the word mod, because that is the divisor. So the number here should not be bigger than the number here. So 5 now goes here. How many times? What will be the remainder? This one is very easy because it's 5. I know it will go there. If 5 has to go here into this number, then we must have a 5 somewhere so that it gives us 1145. I don't know how many times, but this one tells me that the remainder is 3. That one tells me when it comes to 5, that one is easier. So the remainder must be 3. So instead of writing the whole of this number, you should just write 3 mod 5. Now, we deal with the mod the same way we deal with other integers without mod. That we can add, we can subtract, we can expand, and so on. We can expand, and so on. So for instance, what I mean by expanding, for instance, this thing, somebody can even want to write it like this. Mod 5 plus 23 mod 5. Expanding, that's what I meant by expanding. That's the same way we deal with other integers. When you do that, this part, you have to make it smaller because it's bigger than 5. So you're asking yourself, if 5 were to go there, what would be the remainder? And if 5 were to go here, what would be the remainder? So in fact, the way we normally do even with the integers, you can also factorize. So what you do with integers the same way you do with the mod. There's nothing new here. That's the same way we do with the integers. This gives you 5. And in fact, you can see that what is the remainder if 5 were to go into 5? What is the remainder? If 5 were to go into 5, the remainder will be 0. If somebody else wanted, we'll just have, but you see, I've done this because I was imagining you could be given bigger numbers. But these are small numbers. These are smaller numbers. You can just even add them and get 40. You can just even add them and get 40 mod 5. And if 5 were going to 40, you can see the remainder as 0. The remainder is, of course, 0. It's very easy. This one. So these are smaller numbers. I just did this so that you can notice that dealing with mod is not a very strange thing. We deal with mod the same way we deal with the integers. That you can expand, you can factorize, you can multiply, you can divide, dealing with the mod, just the same way we do with the normal integers without the word mod. Even this one, if you want, you can just add whatever is in the bracket, whatever is inside the bracket, and get 41. Then divide by 4. 4 into 41, and realize that 4 will go there 10 times, and the remainder will be 1. You can just add whatever is inside that bracket. It's 41. Then divide by 4. The remainder will be 1. Or if you want, you can expand. So dealing with the mod is very easy. Once you know how to deal with the integers, I think you can hear me. Is that okay? Can you hear me?
Yes.
Thank you.
Yeah.
Now, I think I had already looked at, I was looking at number G. I had already explained that this G, the same way we did F, you can decide to add these two numbers, get 41, and write 41 mod 4. Then notice that 41 is bigger than 4. Then divide that by 4, 41 divided by 4, and notice that the remainder will be 1. Because 4 would go there 10 times. We are not concerned about how many times it goes there. Our interest is the remainder. Or you may decide to expand, right? 18 mod 4. Yes. Is it Lucia? Somebody wants to ask a question? Okay. Now, so we can expand. This would be 23 mod 4. It's not writing here, I don't know why. Okay. Now 4 into 18. 4 times because of 16. The remainder will be 2. 4 into 23, 5 times, get 20. The remainder will be 3 mod 4. And this is 5, which is bigger than the divisor. It's bigger than the divisor. 4 goes there, the remainder is 1. So this is the answer. The same thing can happen even when you have multiplication. You may decide to multiply whatever is in that bracket and divide by 5 and write the remainder. But sometimes whatever is inside that bracket would be bigger than what your calculator can afford to handle. So in that case, you would then use the knowledge that you can expand. You can use the knowledge that you can expand, because the way we deal with the mod, the same way we deal with other integers. These are smaller numbers. This one, your calculator can afford, can handle this. So you can multiply this using a calculator, divide by 5, and then note the remainder. But in many cases where this number will be larger. So if those cases arise, then you just write this as 19 mod 5 multiplied by 288 mod 5. So 19, 5 goes there 3 times. The remainder is 4. And then 288, 5 going there, I can see because this is 8, the remainder will be 3. 5 will go there, the remainder will be 3. This you just use your calculator. And so what is this? Mod 5, what is this? This is 12 mod 5, which is bigger than 5. So divide by 5, the remainder is 2. So in fact, this is a smaller number. If you are to multiply this number and then divide by 5, you would get the remainder to be 2. Even if somebody was to square this, again, you just use the same reasoning. That we deal with this same way we deal with the integers. So that squaring should not now scare us or make it look complicated. It's not. Squaring cannot make it complicated. We just deal with it the same way we deal with integers. So this number could be bigger than your calculator can handle. So in that case, we would then write, and there's something I know. There's something that I know. For instance, if you have a number, let me say 20, and if 4 goes there, now let me talk of 3. If 3 goes here, the remainder that you get, what is the remainder here? The remainder here is 2. The remainder here is 2. 3 goes there, the remainder is 2. So if I was to take 20 square and divide by 3, the remainder that I get will be the same as 2 square divided by 3. The remainder that I get will be the same as that. Let me use a smaller number so that we can do that example. Let me use a smaller number. Let me use 8, which is a smaller number. If 8 were to be divided by 3, if 8 were to be divided by 3, the remainder will be 2. If 8 square were to be divided by 3, I expect the remainder to be 2 square. To be 2 square, which is 4 mod 3, which is 1. I expect the remainder to be 1. If 8 square, you see, if 8 is divided by 3, the remainder is 2. So what I'm saying, if 8 square will be divided by 3, the remainder will be the same as the remainder when 2 is squared and divided by 3. So of course, this will be supposed to be 64. 64 divided by 3, 2, because of 2, what have I written? It's supposed to be 2, then this is 6. Then you bring this one down. Then 1. The remainder is 1. You can see that's what I was just doing. That's what I was doing. What I was doing is, instead of squaring this number and dividing by 3, and knowing that sometimes you could be given a bigger number, which when you square, your calculator may not handle. Just do away the square bit and then divide the number without the square. And know that the remainder when you square will be the same as this earlier remainder squared and then divided by 3. I think I'll repeat that if there's somebody who did not get it later. If after doing the example I, then I'll repeat it. Let's look at this example I. Example I, want to continue the same notion that we deal with mod the same way we deal with the integers, so you can expand. You can expand, and what do you get when you expand? Mod 4 times 13 square mod 4. And remember, we can be given a number which is bigger than 11, a bigger, very big number, which when you square, you would get a number that your calculator will not handle. So we just do the 11 first of all. Ignore the, for a moment, ignore the square for just for a moment and take this 11 divided by 4. What is the remainder? 3. And what about this 13? Ignore the square, although we shall bring it later. Ignore the square, divide 13 by 4. The remainder will be 1. Oh, this was cubed. This was cubed. Now bring those squares. Bring that cube. So what do you get here? 9. And what about here? 1. But this is bigger than 4. So it can also be 1, the remainder, times 1. We can factorize this. It's 1 times 1 mod 4, which is 1 mod 4. Okay. Any question up to there? And the good thing is that it's recorded so that, is it really recording this time? This time? This time it's not recording.
It's recording.
It's recording, huh?
Yes.
Oh, I can't see it from my side. I normally see it. Okay. Now, so we look at another example, unless somebody has a question. We've been talking about remainders. And it's the same thing I want us to continue looking at. The remainder is what is very important when you're looking at modular arithmetic. The remainder is what is very important. So this person takes that 5, raises it to 2024, then divides by 17. He's asking us the remainder. What is the remainder? But there's something we know. Something we know, we've already introduced it in example I above. Example I above, we said we can ignore the power for a moment. Ignore the power for a moment. Then divide this number by 17 and note the remainder. So the remainder, when this number is divided by 17, is the same as the remainder when this number is divided by 17. Is the same. We've seen that in example I. That the remainder when this number is divided by 17 is the same as the remainder when this number here is divided by 17. And of course, we know that 1 raised to any number would be 1. Would be 1. 1 raised to any number would be 1. So that is the remainder. That is the remainder. So, you know, this one, maybe a calculator cannot accommodate it. But that is how we do it. I was trying to imagine how a program can be written. An algorithm can be written so that gives us this remainder. As I try to think about it, I know you also think about it because we want to have a scenario where it's giving us this. So how do you program? You think about that. That we can be doing this. We can be given a very big number here, raised to a very big number here, and we are getting the remainder. Of course, I showed you this using the fast powering algorithm. But of course, there are so many ways of doing it. Fast powering algorithm, we looked at that, is another way of doing this. We looked at it even on Thursday. We revised that. The fast powering algorithm is another way of doing this question. But the other way that I tried to look at here was trying to the other way that I was looking at it is trying to work with this number to give you a smaller number that we can handle, like 1 or -1. If you can think of how can I get 1 or -1 from this, then it becomes very easy. Of course, yes. Okay, let's look at this other example. So I was thinking of that, you see, like this 27, these are easier numbers to deal with. But we have numbers that we cannot reduce to 1 or -1. If we cannot reduce to 1 or -1, then we have the fast powering algorithm, which we learned. We have the Fermat's little theorem, which we learned. We have the Euler theorem, which we learned. And the fast powering algorithm, the successive squaring. The successive squaring algorithm that we looked at will also give us. But let's look at this. Our divisor is 14. We divide 14 into 27. Ignore the power for a moment. Divide 14 into 27. The remainder is 13. 13 is very close to 14. 13 is the same as, is congruent to 1, negative 1. 13 is congruent to negative 1. I just subtracted 14 from 13 and got negative 1. And I'm claiming that 13 is congruent to negative 1 mod 14. And of course, when I do that, what comes into your mind is the definition of congruence, that I'm implying that 14 can divide the difference. This is what comes to your mind. And it's very true that 14 can divide. This is 14 also. It's 14. 13 minus 1 is 14. And of course, you can see that 14 can divide 14. So what I'm saying, 13 is very close to 14. So in fact, it can be written as 13 is congruent to this, can be written as negative 1. And I said ignore the power for a moment. Is the same as that. You can now bring the power back. When you bring the power back to a negative number, you put it inside the bracket before you raise it to that power. The power that we have is an odd number. A negative number raised to an odd number. The result is negative. But in this case, it's not just negative, it's negative 1. In this case, it's negative 1. Negative 1 here, remember the number before the mod is supposed to be positive. We found it to be negative 1. How does it become positive? 13. 13 mod 14. Just ask myself, using the same knowledge I showed you earlier, I just divided 14 into negative 1. And I assumed I'm dealing with a positive number 1. 14 goes there, 0 point. I take the next whole number, which is 1, give it a negative sign. Multiply that negative 1 by 14. Get negative 14, and then subtract, get 13. That's what I have here. The other way I showed you in the class was just to add this to that. That's the other way I showed you in class during one of our revision times. Just add that to that. So we found that 27 raised to 1001 mod 14 will be 13. So in other words, the remainder on dividing this number by this number, the remainder is 13. That is what this question means. Because whatever comes up before the word mod is supposed to be the remainder. So this question is asking us, although the word remainder is not here, but we know that whatever is before the word mod is supposed to be the remainder. So we know that the question is telling us that what is the remainder when this 27 raised to 1001 is divided by 14. And this is what we've just done. And of course, I said we could also use other methods at our disposal. We have several other methods when we get time, we shall again be looking at them in a revision with the time, as time goes by, that you are familiar with them. But as we do it again, the idea is always after you've done this, think of how do we then put it in a program. So because we looked at this fast powering algorithm on Thursday, I'll not look at it today. No, okay, I'll do, but not using the fast powering algorithm. Maybe I look at another method. No, let me just go to how to solve some equations, congruence equations. Let's go to how to solve congruence equations. Please, let's look at this. So that as we do this, as we solve these congruence equations, we are not just solving congruence equations, we are also in the process solving the Euclidean algorithm and the extended Euclidean algorithm. Because while solving this, we use the Euclidean algorithm first, and then you use the extended Euclidean algorithm to find the value of x. So while looking at this, revising this, we are revising several things at once. We are revising the Euclidean algorithm, we are revising the extended Euclidean algorithm, and of course, we are also revising how to solve this type of equations. I just want to solve the first one and then solve the second one. Now, the first one says, okay, the way I did this, because it's a small module, we began by using what we called trial, because we know what mod 8 means. Mod 8 means these are numbers less than 8. These are numbers 0, 1, 2. Just a minute, let me write it properly. When you talk of mod 8, let me talk of mod M first of all. When you talk of mod M, what do you mean mod M? Just mod M. There's no number here. I've not written any number here. Mod M, yeah. What numbers? We are talking of numbers 0, 1, 2, 3. These are numbers all the way up to M minus 1. M minus 1. So when the module is this small, this one I think it's even easier. When the mod is small numbers between 0 and 7, and see which ones on after multiply by 5, on division by 8 would give you a remainder of 3. I think that one can even be easier to write a program. It can even be easier. Because just try telling this computer. I think it can even be easier. You try it. Is it hard just to tell it that I want a number between 0, 1, 2, all the way up to 7, which when it replaces this x and then the result multiplied by 8, divided by 8, the remainder will be 3. So that it just tries 0. Just tries 0, multiplied by 5, and discovers that the remainder is not 3. Because this will be 0. 0 divided by 8, the remainder will be 0. Then it tries 1. then finds that 1 times 5 will be 5. Divided by 8. 8 will go into 5 0 times, and the remainder will be 5. So that this is not congruent. No, okay, it's 5. Just a minute, let me just write properly. It finds that this thing, when multiplied by 5, the answer is 5, but the remainder is not 3. So it's not congruent to 3. And of course, before you do that, you should have told this computer that before you do this type of question, first of all, try the GCD and see what the GCD of 5 and 8 is. And also see if this GCD can divide the number before the mod. You have told this program of yours. You have told this program that before you do this question, first of all, check the GCD. If the GCD can divide the number before the mod, then it means this equation has a solution, or it has solutions. So the number of solutions will be, of course, equal to the GCD. The number of solutions will be equal to the GCD. So in this example that we are doing, the GCD is 1. So you're only expecting, and of course, 1 can divide 3. So we are expecting one solution. So we are now trying to see which one is a solution. And what are we trying? We're trying numbers from 0 to 7. One of them will be a solution. Let's try 2. This gives us 10. On division by 8, this is 2. And you can see that it's not congruent to 3. So 2 is not a solution. Try 3. 5 times 3, yes, I'm right. It's not writing here. 5 times 3 will be 15. On division by 8, the answer is 7, which of course is not 3. So it's not congruent to 3. Try 4. This gives you 20. And of course, yes, that's 20. On division by 8, the answer will be 4. The remainder will be 4, which of course is not 3. So 4 is not a solution. 3 was not a solution. 2 was not a solution. 1 is not. Let's try 5. That is 25. On division by 8, the remainder is 1, which is not congruent to 3. Let's try 6. That gives us 30. Or if you don't want 30, since you are dividing by 8, you can say it's -3 times -2, which is 6. So the remainder is 6. The remainder is 6. Somebody could be asking, where did I get -3 and -2 from? And I will refer that person to my mod, which is 8. So I'm just saying positive 5 is the same as -3. Mod 8 and 6 is the same as -2. Congruent, it's congruent to -2. Mod 8. I just subtracted 8 from each of these numbers. 8 from 5, 8 from 6. That's what I got. And so it gives me the remainder of 6, which is not congruent to 3. I'm only left with one value to try this time. Let me try it. 5 and 7. And of course, if I was to use, you see, I'm using this knowledge here to make my work easier. So because I'm dealing with the mod of 8, this same as, of course, this same as -3 times -2 times -1. -3 times -1, which of course is 3. And you can see that this is congruent to 3 mod 8. So that means 7 is the solution to the equation that we're given. So if you don't want this method that I consider easy, you can just multiply these two numbers, get 35 divided by 8, 8 into 35. 8 times 4 is 32. 32 from 35 is 3. You'll have gotten the same result. That is where I think I should just stop, because so that we receive questions if there are any from you. Ask questions so that we can respond, or if you have some input, somewhere you feel that it can also help. There's an example or something, an explanation. You can do that. But for me, that is where I stop.
Thank you, Dr. Sakwa. I think personally, the revisions are very welcome, and I can see we are moving on swiftly. And also from feedback from the lab, I think people are very we're excited about the revision. So let's continue tomorrow. Or that should be on Tuesday tomorrow. Yeah, if no questions, I think we can call it a night and see you all tomorrow. Thank you.